Post Correspondence Problem, or PCP, is an essential problem in computability theory and, importantly, an unsolvable problem. PCP is named after Emil Post and is a foundational problem in computability theory. It is one of the earliest examples of an undecidable problem and is used to prove other problems are also undecidable. The PCP is defined by two lists of strings, A and B. The goal is to find a sequence of indices so that the concatenation of strings from list A equals the concatenation of strings from list B using the same indices in the same order. Indices can be repeated. We can visualize PCP using dominoes, where the top string is from list A and the bottom from list B. For example, the index sequence 214 produces BABBA for both the top and bottom strings. Here is an easy example with 5 string pairs. The sequence of indices 1, 2, 3, 2 provides a solution, where both concatenations produced are equal. This is a medium example with 4 pairs. The sequence 1, 2, 2, 3, 3, 4 is a solution, producing the same long string of A's and B's for both lists. Notice that this solution uses 6 tiles, repeating indices. Here's an easy instance with no solution. In this case, every string pair starts with different letters. Consequently, any concatenation will start with different letters, meaning a match is impossible. This instance also has no solution. Every string in list A is longer than its corresponding string in list B. Therefore, any concatenation from A will always be longer than the corresponding concatenation from B, preventing a match. So far, we have seen instances which were all decidable. We note that being able to conclude that there is no solution is also deciding that instance. However, in the general case, PCP is undecidable. This means no algorithm can solve all possible instances. For some instances, we can neither infer that there is no solution, nor can we find a solution. This is a fundamental mathematical fact, defining hard limits on what can be computed. The unsolvability of PCP is typically shown by reduction from the halting problem. This involves encoding Turing machine configurations as string pairs. The original proof, however, used the concept of a normal system. The reduction from halting problem involves constructing tiles that encode transitions of a Turing machine. A matching PCP solution is equivalent to a valid halting computation sequence. Thus, if the Turing machine halts, the PCP instance has a solution. Otherwise, it does not. The key insight is that PCP can simulate any computation. Deciding PCP would therefore imply deciding the halting problem. Since the halting problem is undecidable, PCP must also be undecidable. As a consequence, many undecidability results reduce from PCP. While classic PCP is undecidable, some variants, like bounded or modified PCP, are decidable. PCP demonstrates fundamental limits of computation. In summary, the post correspondence problem asks for matching string concatenations from 2 lists. It is undecidable. A proof of its undecidability can be shown via reduction from the halting problem. PCP remains a cornerstone problem in computability theory. For those interested in the history, the original reference by Emil Post was published in 1946.